Yes, so far all movement that we've dealt with has had one thing in common. The acceleration has been constant. So when we did SUVAT, when we were talking about horizontal and vertical motion, the acceleration was constant. When something is falling, it is constant because that's due to gravity, which is largely constant on this planet anyway. And in the situations where we were using Newton's third law and F equals ma, where we had an unbalanced force, the resulting acceleration was also constant. And we need to answer all sorts of questions that revolve around constant acceleration. However, we also need to deal with situations where that acceleration is not constant. So these next couple of lessons are going to be talking about variable acceleration. And I'm going to spend the week talking about three quantities which we've already talked about. Displacement, which we tend to use S to deal with, or I think we're going to come across it being described with an X today as well. Velocity, which we use V and sometimes U to stand for, and acceleration. And whereas we're used to displacement and velocity varying, because with constant acceleration, if it's a positive acceleration, the velocity is getting bigger, and displacement is changing all the time as something moves. We haven't come across a situation where acceleration is variable just yet. In questions that involve variable acceleration, they nearly always start with a formula for one of these, and that formula is generally just stated without any justification. So this example here is one such example where we are told that a body moves in a straight line, no mention of constant acceleration, so we can't use SUVAT in this question, but we're told that its displacement is given by this rather convoluted cubic formula. S is equal to 3t cubed minus 3t. Now we're not told why this body is moving where its displacement relates to that. We don't know, and we don't have to worry about it. Remember, displacement is a vector, so we're not talking about the distance travelled, we're talking about how far it is away from where it started. Okay? So see if you can answer those two questions, A and B, using that formula. Would anyone like to borrow a calculator? Right, you'll have to share with Alpha, and did I bring both? Did bring both? Oliver, do you have a pen for this class? So, as long as you give it. I said I've no calculator or pen. I somehow would you believe me if I said it doesn't work after? Leave them next to the mirror and the hair products. I'm sure you'll remember them. Just your haircut.
It's prune.
It's prune.
Is that always true, or is it just for this question?
Just for this question. Just for this question. So this is just algebra, nothing complicated going on here at all. This is just algebra. And the units will be hidden in there sometimes. Normally we're dealing with displacement in meters, velocity in meters per second, acceleration in meters per second squared. So for A, I'm just substituting t as 2 into my formula. For B, when it returns to where it started, its displacement will be 0. Remember, don't divide by t because t can be 0. Instead, we're going to solve this cubic by factorising it first. So on part B, I just asked when does s equal 0. I factorised it, pulled the t out, resisted the urge to divide by t. So I know that it's where it started at t0, that's obvious. But where else? Well, it's when this bracket equals 0. Now, if that was a nice one I could factorise, then I'd be happy, but it's not. So I'm just going to ask, when is that equal to 0? So it's the square root of 3 over 2. That's going to give me a positive and negative answer, but I'm only interested in the positive, so it's the square root of 3 over 2. So it doesn't indicate a level of accuracy, so you could have left it as root 3 over 2, or 3 second figures would be 1.22 seconds. Happy with that? So, there's no mention of constant acceleration, similarly no mention of variable acceleration. But these questions are normally obvious to spot because they start with a formula for one of these three things without any sort of justification. Let's do another example. So in this one we are given a formula for velocity. Again, no justification for that formula. It might help you, well, spoiler, it will help you, certainly for part D, to use your calculator to sketch this one. So you can sketch it using the graph function. Obviously you're going to use y equals 2x squared minus 16x plus 24. But that will certainly help, although we'd still be expected to use algebra to justify that. So have a go at those questions there. Initial velocity is when the time is 0. Yes, so I've sketched the graph. I got it all in the y-axis and then changed the x-axis from 0 to 5. So I can now answer these questions. Remember, we're not really allowed to do this without algebra, but I can answer these questions using my favourite button. So the y-intercept, that gives me the initial velocity, which is 24. But that's easy, isn't it? I just make t equal to 0 in the formula, and v will obviously therefore equal 24. At rest, so that's when its velocity is 0. So again, those are the roots. So it's at rest when t equals 2, but I need to perhaps do a little bit of work to justify that. The t when it, v is 64, well I'm going to do that without the graph, I can do that nice and easily. The maximum speed within that 0 to 5 range, well I know what shape this graph is. It's a parabola, and I know that it starts at 24. So I would just do a little sketch like that and say maximum speed is at the beginning, 24 meters per second. it is going to eventually be going faster in the opposite direction. But I know that at 5, I haven't yet reached that. The graph shows me that. I haven't gone far enough for that to be the case. So I think for D, a quick sketch of what you've got on your screen would be enough. I think that's good enough. So let's just double check then that we can justify the middle two answers. So the initial velocity, I just made t equals 0, that's nice and easy. The values when it's at rest. So we're just solving when is the velocity 0. And we can use our calculator to solve that. I'm going to do it manually just because I don't want to forget my factorising skills. So what have we got? We've got -6 and -2. So it's at rest. Actually, yes, so there were 2 answers for that, weren't there? There were 2 answers because we're not initially given the 0 to 5 restriction. So it's at rest when t is 2 and when t is 6. So that's part B. But you could have used your calculator to solve that. You don't have to do the factorising thing. That's just me trying to keep the brain moving. And then V is 64, so I'm going to make V equal to 64. And it's just a quadratic. I'm going to line it up by taking 64 from both sides. And then I'm just going to solve that. And again, you can solve that with your calculator. I'm going to... so that's 10 and 2.
I'm fixing my calculator.
So I know that the velocity will be 64 when t is 10, but also when t was -2. So that was sort of before we started going. So t is 10 was the answer to part C. Are we happy with that? Right. So let's just do a few questions based on that. Yes. So if we start at question 5 on this sheet, please. Start at question 5. Again, this is taken from the textbook. So question 5 on the sheet, which is actually from page 184, question 5, exercise 11A. Okay. So initial velocity was just when t is 0. You can do that by just looking. At rest means velocity is 0, so I just solved it on my calculator. When v is 5, I just made v equal to 5, lined it up, solved it on my calculator, and then a bit of a cheat here. I sketched it on my calculator between 0 and 2. I already knew it crossed at 4/3 and 2. Sorry, that sketch is wrong, isn't it? And because it's a parabola, its maximum speed will either be at that end or that end, so it's clearly at that end, so that was enough justification for that. You crack on through the rest of those exercises. So we're on, for those at home, page 184, exercise 11A. Okay, so with 6, got an unhappy parabola. So the first part, didn't have to have any understanding of the graph at all. Find the time for it, come to instantaneous rest. That's just when t is 0. So remember, don't divide by t, just factorise. So because t is 0 is a solution, but 4 is the other solution. Your calculator can solve it. You can solve it with your calculator at that point. Now, because I know it's an unhappy parabola, and I know that it has roots at 0 and 4, I know where its maximum velocity will be. It's going to be halfway between the two. So even though I've sketched it and used gsolve, and I already know the answer to B is 8, I can demonstrate that by just saying, right, the maximum speed, I think it says, it does say speed, is when t is 2, because I know that a parabola, I know this is an unhappy parabola, and I know that it's symmetrical. So I just make t equal to 2 in the original formula, and that gives me 8 meters per second. Again, there's no way we can get that wrong. We might lose a few method marks if we use our calculator but don't justify it, but at least you're going to get some marks even if you can't get any further. Yeah, 7 was a clumsily worded one. Big T, I think, is just when it is when S is 0 again, so big T is the other solution, T is 0, T is 3 is the other solution. And got on to 8, then okay, so these variable acceleration questions don't mention variable acceleration. So you've got to be prepared to look out for them, and but they're easy to spot because they'll either give you a formula for S, for V, or for A, which is nearly always a cubic or a quadratic. Now, so far, in a question that's asked about S, we've just worked out values of S or values of T. And in a question where we were asked about V, we've worked out values of V or values of T. But there is a relationship between the three things. And it's a really neat relationship. And it's a relationship that we've already come across at GCSE. At GCSE, we did velocity time graphs. So you might have had a journey with a velocity time graph of that. And we were asked, so that's velocity, we were asked to work out the distance travelled. And you may remember we used the area under the curve. We were also asked for acceleration, and for that we worked out the gradient of the curve. And that's because velocity is the rate of change of displacement. If you've got a formula for displacement, you can convert it into a formula for velocity by differentiating. Velocity is the rate of change of displacement. And acceleration is the rate of change of velocity. So if you've got a formula for velocity and you differentiate it, dv by dt, that gives you acceleration. And it's even better because if you've got a formula for displacement, you can differentiate it once to get a formula for velocity and again to get a formula for acceleration. And we already know, don't we, that differentiation has an inverse operation. So if we want to work out velocity and we know acceleration, we just integrate our A formula with respect to time. And if we know velocity and we want to work out displacement, we just integrate velocity with respect to time. So these three quantities, displacement, velocity, and acceleration, are linked using differentiation and integration. And this is a really nice place in the syllabus where what we do in mechanics backs up what we've done in pure math. So it's a really good opportunity to practice those two skills. So understanding and remembering this relationship is really important, and making sure you're going the right way. Velocity is rate of change of displacement, so I differentiate my displacement equation. Acceleration is rate of change of velocity, so I differentiate my velocity equation, or I differentiate my displacement equation and then differentiate it again. So let's look at some examples of this. I specifically said, just checking the notes, sorry, which one I'm going to do. Example 4. So rather annoyingly in this example they're using x for displacement. I don't know why. I'm going to ignore that and use s. So we've got a formula for the displacement, s meters, and we are asked to find the velocity, and we're asked something about when the velocity is 0, and we're asked to find the acceleration. So what I'm going to do before I answer any questions is I'm going to take my S equals formula and differentiate it, which will give me a V equals formula, and then I'm going to differentiate it again to get an A equals formula, and then I'm going to answer the question. I invite you to do the same. So it's not ds by dx, because t is the variable, it's ds by dt. So when we are differentiating, we're multiplying by the power, reducing the power by 1. So having differentiated and then differentiated again, we should be able to answer the rest of the question. Have a go. Yeah.
Is it during this that the number disappears?
Yes, the 12 disappears, yeah, that's right. So I differentiated to get a formula for velocity, and I used that to answer A and B. So for A, I just made t equal 3 in my expression and got 76 meters per second. And for B, I just made V equal to 0 and added 32 divided by 4 cube root. It's got t is 2. Last question was about acceleration, so I took my V equals formula and differentiated it again, and then just made t equal 1.5 to give me 27 meters per second squared. So over the page on the sheet, you've got questions 2 to 6, which for those at home are on page 186. 186. Questions 2 to 6, and yeah, we might make a start now and we'll finish those tomorrow.